So we've seen that Type 1a supernovae may be the thing that happens when you exceed that magical Chandrasekhar limit, where the Heisenberg uncertainty principle and the pressure it provides is exceeded in the case of a white dwarf star. Uh, it fits the sort of places that these things should occur in galaxies. The objects don't have any hydrogen that you might expect from most stars, and they sort of provide the right amount of energy that you might expect. So, from that perspective, it looks all pretty good.
But there is a problem, as you've just mentioned in the last video. How do you get these overmassive white dwarfs in the first place? You said one class of models involved a binary system, so another star is dumping gas on the surface. But in that case, where did this other star go? No one's found these other stars left lying around in the murder scene. But if it's not that, if it's a merging of white dwarfs or something like that, then how come these things are so beautifully symmetrical?
Yeah, so, this is one of the really big mysteries in my area of astrophysics right now that I have to admit confounds me, even to this day. But we have some ideas. So, one thing is that imagine that you have one star donating material to the other. As the material falls onto the white dwarf, that white dwarf is going to spin up a bit. Now, as it spins up, that centrifugal force actually removes some of the degeneracy and puffs the star up.
So it's more like a frisbee than a
sphere. Like a
sphere.
frisbee, but it also means it's bigger. It means that it doesn't reach that central density necessary to ignite as essentially as a big thermonuclear bomb. So imagine that you are dumping material on, you just run out of fuel, and you have this fast thing spinning that's maybe 1.5 times the mass of the sun. Then it turns out it will slow down over 1 billion years. And when it slows down enough, then it will ignite 1 billion years after the material is donated, allowing that other star to fade away into a white dwarf, so it's essentially impossible to see. So that's an idea. You might have a delay. And very, tricky to go through and show that that's not true, because it doesn't leave much behind. Another idea is that it really is a white dwarf donating material, but the white dwarf is just feeding on this helium, and that helium detonates and the whole thing explodes. Again, the little helium white dwarf donating material, it's not very big and you wouldn't see it easily. So that's another way to hide it. And of course, the white dwarf mergers, that's really hard physics. You got to take two things, with the mass of the sun and mix them together in a period of a second and blow them up. And the explosion itself will tend to regularize the messiness of the situation. Whether or not it can do it enough, I think, is to be determined. And a lot of people, when they do that physics, don't even think the thing blows up at all. They think it might collapse down to something even smaller than a white dwarf, which we're going to talk about here in the future, a neutron star. So I think we have some ideas, but we don't have the answers yet.
And this is one of the most important questions in astrophysics, not only because these supernovae are so damn interesting in their own right, but because they are the underpinnings of much of modern cosmology for your own Nobel Prize work. Whatever these things are, it's their regularity, their standard candle nature that allows us to measure the existence of dark energy. So if we don't really understand what's going on in these things, that surely must cast a doubt on how useful they are. Would you ever really trust a standard candle if you don't understand why it's standard?
Well, at some point, they are a useful tool, independent of how well we understand them, because we can go out and we can try them out all around the universe and make sure that they behave. If I have a whole bunch of light bulbs in a jar, and they don't, I don't know how well the 100 watts is calibrated on them, but I go and I put them all around me, and I see that when they're at the same distance, they're the same brightness. I sort of know that, I don't know if they're 100 watts, but I know they're all the same, and I can use that over time. So it's not a loss. The problem is that if we want to use them to make ever increasingly better measurements, then the subtleties start to matter. And so if you just want to discover that the universe is accelerating, you only need to know things, it turns out, to about 20%. But when you want to measure it precisely, well, then you maybe want to know things to 1%. And at that point, you really do need to know the details. And so we really do need to understand these things better and make sure they're not changing back in time if we want to make sure we have success in the future.
And how do you think we might go about coming to a better understanding of these things over the next decade or so?
Well, I think there's some interesting work that we're doing. So some of the work that we're doing here at the ANU is we're actually able to measure the masses of the things that explode. And one of the interesting features that we're finding is it looks like a lot of them weigh less than the magical Chandrasekhar mass. And this is some work that one of the people who works with me, Richard Scalzo, has done. And it's still early days. We need to convince the rest of the world that's true. So that would be a sort of a smoking gun.
Sort of a cat among the pigeons, I think.
Right, because there's only one way that we have that does that, and that's where you put the helium on the outside and you detonate it. That's the real only way to do that. But that work also shows that a lot of them are also at least 1.4 times the mass of the sun. So maybe there's one or two ways of going. You know what I think maybe the best way to do it's going to be is at some point one of these things is going to explode in our Milky Way or one of the nearby Magellanic Clouds again, and then we're just going to be able to see what happened. And I think if I really had to bet how we're going to be absolutely sure, it's probably going to be that.
So, we've seen white dwarfs as part of the violet universe. It started off with the dwarf novae, the little baby explosions of these things due to the accretion disk, and then we've gone up to the classical novae when they had a flash on the surface, and then we've gone all the way up even more in energy to the type 1a supernovae. So these white dwarfs are pretty violent things. Is that it then? Is the violet universe finished? Course over?
Well, when we were out looking at the history, there was more than one way it seemed to blow a star up, because there were stars that didn't have hydrogen. There was that whole class of stars that did. And those don't seem to necessarily be a white dwarf exploding. So it seems the indication that there is more than one way to blow a star up.
So we're going to need something else, Violet, something even worse than white dwarfs. And that's the topic of the next video.